Hello. In this lecture, we'll define hyperbolic groups and then we'll prove that a hyperbolic group is finitely presented group. Let us begin with the definition of hyperbolic group. We'll see examples also. Let G be a finitely generated group. The group G is said to be hyperbolic group or word hyperbolic group if the Cayley graph of this group with respect to some finite generating set S is a delta hyperbolic metric space for some non-negative number delta. So corresponding to a finitely generated group, you can construct a Cayley graph. If that Cayley graph is a hyperbolic metric space, we say that that group is a hyperbolic group. Now there is a question of well-definedness. So there can be many generating set of the finitely generated group G. Suppose S prime be any other finite generating set of this group G. We already proved this fact that the Cayley graph of G with respect to S is quasi-isometric to the Cayley graph of G with respect to the generating set S prime. And in the last lecture, we have proved that hyperbolicity is quasi-isometric invariant. So hence, if the Cayley graph gamma GS is a hyperbolic metric space, then the graph gamma G S prime is also a hyperbolic metric space. So therefore, this definition is well defined. So in the sense that if I change the finite generating set, then the Cayley graphs for all those finite generating sets will be hyperbolic metric space. So for example, if I take free groups of any brand, so these free groups are hyperbolic groups as their Cayley graphs are trees. And now if I take a closed orientable surface of genus G, where G is greater than or equals to 2, so we have seen that the fundamental group of the surface acts properly discontinuously, freely, and co-compactly by isometries on the unit disk model of the hyperbolic plane. So that is the Poincare disk. So now by Milnor-Swartz lemma, if I take a Cayley graph of this fundamental group with respect to some finite genetic set, so this will be quasi-isometric to this Poincare disk. And Poincare disk is a hyperbolic metric space, and hyperbolicity again, it is a quasi-isometric invariant. So therefore, this Cayley graph of this fundamental group, so this will be a hyperbolic metric space. So therefore, fundamental group of genus G surface, where G is greater than or equals to 2, is a hyperbolic group. Okay. So next, what we are going to prove that these hyperbolic groups are finitely present. So first of all, recall the definition of finitely presented group. So a group is said to be finitely presented. So if there exists a finite generating set S and a finite relation set R such that this group is this quotient group. So it is the quotient of the free group generated by S, and in the denominator, so this is the normal closure of the set R, where R is a finite set. So now note that if I take any element R belongs to this normal closure containing this R, so then So there exist finitely many elements R1, Rn in R such that this R is product of this conjugates of this Ri. So R is equal to product of this xi, Ri, xi inverse, where I is running from 1 to n. And conversely, if an element can be written as product of this conjugates, so this R will belong to the normal closure containing this set R. So this is a simple observation. So this you must have learned in book theory. Now, so this is my theorem. So a hyperbolic group is finitely present. By definition of hyperbolic group, the group G is finitely generated, and let S be a finite generating set of G. So first of all, note that an element in G is a normal closure if and only if that element is identity element in G. So suppose if I take an element W which belongs to this denominator, that is the normal closure, so then that element will be an identity element in G. And also the converse is also true. So if I take an identity element in G, so this means that that element will belong to this normal closure. So therefore, so there will exist R1, R2, Rn in R such that this W can be written as the product of these conjugates xi, Ri, xi inverse. Now let us take this W to be equal to A1, A2, Am, where this AI, it belongs to this this generating set. So AI, either AI belongs to S or AI inverse, it belongs to S. So that is the meaning of this. So either AI belongs to S or AI inverse, it belongs to S. So W is A1, A2, Am, where this AI, it belongs to S union, S inverse. Okay. So because this W, it is equal to 1, it represents a loop. So this is my loop, which represents W. So W starts from 1, and this is an edge in the Kelly graph. So the first vertex is V1, and there is an edge between 1 and V1, which is labeled by A1. The next vertex in this loop is V2, and there is an edge between V1 and V2, which is labeled by A2. And you can proceed similarly. The edge between this Vi and Vi plus 1 is labeled by Ai plus 1. So now what we do, so for this vertex Vi, so we take a geodesic Ci joining this identity element and Vi. So this is my geodesic Ci, which is joining 1 and Vi. So you do this for all the i's. So we'll get this geodesics here. And now note that, so distance between Vi and Vi plus 1. So this will be at most 1 because the length of this edge, so this is equal to 1. Yeah. So that is an observation. And now what we do, so let Cij be vertices on Ci such that distance between Cij minus 1 and Cij is equal to 1. So we can split this geodesic. So this geodesic Ci the following way. So first you take Ci1 such that the distance between 1 to Ci1 is exactly equal to 1. So distance between Cij minus 1 and Cij, so this will be equal to 1. And at last, suppose Citi is Vi, the earlier vertex what we will get. So this distance will be at most 1. Yeah. Okay. Yeah. So note the following thing here. So this Vi, it is a vertex. So the distance between 1 and Vi, so this will be a natural number. So therefore, so this distance, it will be not at most 1. It will be exactly equal to 1. So distance between Cij minus 1 and Cij is equal to 1, where j is equal to 0, 1 to T I here. Okay. So this thing you do for all these i's. So we'll have this picture here. So we'll get this picture. And now what you do, so you join this Ci1 and Ci plus 1, 1 by this geodesics. So these are my geodesics. Yeah. So these are my Cij and Ci plus 1j. So join this by a geodesic, which is leveled by Aij. So this is leveled by Aij. Okay. So now consider the word Ci Ai plus 1, Ci plus 1 inverse. So here the Ci represents a geodesic word. Yeah. So you take this word here. So first travel up to Ci, then Ai plus 1, and then return back by Ci plus 1. So we'll get a loop. So Ci Ai plus 1, Ci plus 1 inverse. So this will represent a loop in the calligraph. And also take the C1 to be equal to A1 and Cm minus 1 to be equal to Am and Cm to be equal to 1. So now note that, so this W, so this is equal to A1 C1 inverse, C1 A2 C2 inverse, C2 A3 C3 inverse, Ci Ai plus 1, Ci plus 1 inverse up to Cm minus 1 Am. So what we have done here, so first we have started with this loop W, and this loop W you can write as a product of some subloops. So this is another loop. So this is my Ci minus 1. So you go up to here, and this is my Ai. You travel by Ai, and then you come back to 1. by this Ci. So we'll have this loop here, and so W is nothing but product of all this kind of loops. So there will be some minor change at the initial beginning point and the end point. So that thing I have written it here. So at the starting point, the loop will be A1 C1 inverse, and at the end it will be Cm minus 1 Am. Okay. So now length of each AI is 1. So length of this loop A1 C1 inverse and Cm minus 1 Am. So this will be at most 2. Because C1 is A1 and Cm minus 1 is equal to Am. So this will be at most 2. And now what we'll show that? We'll show that this each of this loop is product of the form US RS US inverse. It is a finite product where this R1 R Li, so this belongs to a finite set. So this Rs, it belongs to a finite collection. So if you can do that thing, so then this word W is product of finitely many conjugates. And from that, we'll get this group to be finitely presented. Okay. So next goal is to prove this thing. So each of this subloop, so this will be equal to this finite product of this conjugates. So we need to find this Rs. So now consider the triangle 1 bi plus 1. So now consider this triangle. So this is my triangle. This triangle. So this triangle is delta thin and length of AI plus 1 is 1. And Ti, so what is Ti? Ti is the length of the geodesic Ci, and Ti plus 1, it is the length of the geodesic Ci plus 1. So now one can prove that for j less than equals to this minimum of this Ti and Ti plus 1, distance between Cij and Ci plus 1j, it is less than equals to 2 delta plus 2. So this will follow from this observation. So let us begin with a delta hyperbolic metric space. So let us take X to be a delta hyperbolic metric space. And now let us take two geodesics, this alpha and beta, where the endpoints of alpha, so this endpoints, so they are at most one distance apart. And this alpha and beta, so they are starting from this point P. So now if I take this point beta T, so there exists a point either here or on this geodesic such that the distance will be less than equals to delta. Suppose there exists a point here, so this distance is less than equals to delta. So then, because this length is at most 1, the distance of this point beta T to this endpoint of this alpha, so this will be at most delta plus 1. So therefore, so there will exist some T prime such that alpha T prime, distance between alpha T prime and beta T, so this will be at most delta plus 1. And now, using triangle inequality, so you can prove that distance between alpha t and alpha t prime. So this will be at most delta plus 1. And now if I take alpha t here, this is my beta t. The distance between alpha t is less than equals to 2 times delta plus 1. So using this thing, so we can prove here, so distance between Cij and Ci plus 1j, so this will be less than equals to 2 times delta plus 1. So now, as I said before, so join this Cij and Ci plus 1j by geodesic Aij. So this is my geodesic, which is labeled by this Aij. So length of this geodesic, it is at most 2 delta plus 2. Okay. And now let us consider the words xij to be equal to Cij inverse Cij plus 1. And let us take this Rij to be equal to Xij times Ai j plus 1, Xi plus 1 inverse j Ai of j, and take the inverse of this thing. Okay. So what we have done, so let us go back to this picture. So this geodesic, it is labeled by Xij. That is labeled by Xij from here. And what is my Rij? So Rij, it is the following. So you start from here. So first travel Xij, then Aij plus 1. Then follow this geodesic, and at last follow this Aij. So Rij will be this loop. Yeah, so Rij is Xij, Aij plus 1, Xi plus 1, J inverse, Aij inverse. Where this J is greater than 1 and less than minimum of this Ti and Ti plus 1. And for Ri1, it is nothing but Ci1, Ai1, Ci plus 1 inverse 1. And now let us take this Ri to be equal to Ai plus 1, Bi plus 1 inverse, Ci plus 1 Ti, and multiplied by Ci plus 1 Ti inverse Bi. So if this Ti is less than equals to Ti plus 1. Okay. So now note that length of each of this Rij or Ri, so it is at most 1 plus 2 delta plus 2 plus 1 plus 2 delta plus 2. So let us consider this picture Rij. So this length of this Xij, it is equal to 1. Length of this geodesic Aij plus 1, this is at most 2 delta plus 2. Length of this geodesic is exactly equals to 1, and length of this geodesic Aij, it is at most 2 delta plus 2. So therefore, length of this Rij, so this will be at most 4 delta plus 6. Similarly, you can prove that this length of this Ri So which appears at the end. So length of this Ri, it will be also at most 4 to the power 6. Now let us take this R to be the set of words in G of length at most 4 to the power 6. Now because this group G is finitely generated, so this R is a finite set. And each of this Rij, Ri1, and Ri, it belongs to the set R. Now we are almost done. So now what you do, so let Uij be the word representing the geodesic joining 1 and Cij. So Uij is this word representing the geodesic joining 1 and Cij, this green geodesic. Okay, and now consider consider the word Uij, Rij, Ui, J inverse. So first travel by Uij, and next you travel this loop Rij, and then again you come back to 1 by Ui J inverse. Uij inverse, yeah. So you come back by Uij inverse. Yeah, so we have this picture here. So now you can check that. So this Ci Ai plus 1 Ci inverse. So this whole loop is the product of this loops. This Ui1 Ri1 Ui1 inverse dot Uij Rij Uij inverse, and at last Ui minus 1 I Ri Ui Ti inverse. Now each of this loop is finite product of conjugate of elements of this R. So this Ri1, Rij, and Ri, it belongs to this finite set R. And W is the product of the Ciai plus 1, Ci plus 1 inverse. And each of this thing is finite product of the conjugates. So therefore, W is a finite product of conjugates of elements of R. And because R is a finite set, so we have proved that this group G is a finitely present group. Okay, so I'll stop here.